Alright, notice that for each of these problems that all of the problems have logarithms of the same base and that they're not being switched around. So for the first one, you'll notice that there's addition, and addition is going to be multiplication. So we have log base 2, and I'm going to take this 5, multiply it with the 3, multiply it with the x, and they're all being multiplied because they're all being added. We could go ahead and simplify this further. The 5 times 3 is a 15, and that's our answer for that one. You'll notice that this is multiplication, and then this is division. Notice how the division is at the end of the problem. So all the multiplication comes at the beginning, and then we go ahead and put it all the division at the end. And if the problem isn't set up like that, you're going to want to rearrange it so that it is in that order. So then these will indicate division. In other words, this will be in the denominator. However, you also have to consider that there is this little number in front of this log that goes up as a power. I'm going to make a fraction, and all the pluses are going to go on top, and the minuses will go on the bottom. This 3, we use the power rule, so it went back up to the z. That exponent only belongs to the z. It had nothing to do with the y or the x. Speaking of, I forgot an x. Thank you for that. 5 is being multiplied with this x right there. That is a complete solution for part B. And I shouldn't even say solution because we're expressing this logarithmic expansion as a single logarithm. So notice that we eliminated all of these logarithms. There were 4 logarithms, and now it's being expressed as a single logarithm by itself. You're going to notice this 5 goes back up to the x as a power. This 1/3 goes back up to this quantity as a power. And this 3 goes back up to this x as a power. However, you'll notice that the pluses and minuses are mixed around. So like I mentioned before, you're going to want to make all your pluses go at the beginning, and then all your negatives go at the end. So I'm going to rearrange this. Actually, I'm going to rearrange it and start putting the exponents back up. So you'll notice that I put this 5 back onto this quantity, this 1/3 as a power back up to that quantity, the 3 back up to the x, and I also moved it to the front. And why did I do that? Because it's a plus. I want all the pluses to be at the beginning, and then I want my minuses to be at the end, and the only minus that I have in this case is minus natural log 5, and that's why I put it at the end. Okay, so now what I can do is I need to recognize that because these are all additions, they end up being multiplications. This is going to go to the denominator. Why is it not a negative 5? Why is it a positive 5? Because the minus indicates division. In this case, it indicates a denominator. Now, we're not done with this problem yet, because I have to simplify this still. You'll notice that these are the same variable, and so I can add the, if I'm multiplying these, I can add the exponents. I'm going to express this as a cubic. And that's the answer. This is going to be the opposite. This is going to be kind of like distribution, but it's not. So notice that there's a multiplication going on and a power. But this power only belongs to the x. It does not belong to the 3. So if we had this, for example, then the 2 belongs to both of the terms inside. If we have this, however, it just belongs to the x only. So for those of you that are uncomfortable with this, 3x squared means 3 times x, whereas 3x squared means 3x times 3x, which ends up giving you 3 times 3 times x times x. So there's a difference there. So this ends up being log 3 plus log x squared. However, this 2 is going to go ahead and jump in front. We get log 3 plus 2 log x for part A. For part B, we need to recognize that this is a 1/2 power. And that means x to the 1/2 and y to the 3/2. I can split this up because this multiplication is addition. Again, be flexible because this is different math. This is not your usual algebra. This is a more of a rearranging, right? And then, so we've gone ahead and done the multiplication. Now we're going to do the powers, right? These powers go in front. And finally, this last one. This last one's a little complicated. So, one of the best things you can do with problems like these is to look at what's happening and then write the opposite, right? So we see, for example, that 3 is being multiplied by x. So that means it'll be an addition. You'll also notice that this 5 belongs only to the x. There's a power. This 2 belongs to the y. There's a power. This square root has a 1/2 power. It's being multiplied. But is there going to be addition? Because it is all a denominator. So these are going to be minuses, right? And then this will be a plus right here. So we're going to end up seeing a plus and a minus and a minus. This is the natural log. So what we have here is natural log of 3x to the 5th minus natural log y squared minus natural log radical z. I thought I'd go ahead and just show you what to do with the denominator first. Now let's go ahead and do some more work. This 3x squared, I'm going to separate it into 2. This z to the square root, I'm going to express it as an exponent. I'm going to go ahead and drop exponents in front where appropriate. This 5 goes in front of this x. This 2 goes in front of this y. And this 1/2 goes in front of this natural log of z. I leave it to you as a good exercise to take our answers that we got and to be able to work them backwards to the original problems. Same thing for problem 3. It would be a good exercise. Recall that when we evaluate logs, we set them equal to 0. Set equal to x. Let's go ahead and use ELB. Recall that the exponent is the logarithm of the base. So the exponent is the x right now. The base is 2. And there's the argument. This should remind you of problems we've done in the past with exponentials, right? I can use a factor tree to express 32 in terms of base 2. And then you will recall that if the bases are the same, the exponents are equal to each other. So for A, we get that x is equal to 5. For B, recall that this is a common logarithm. So what we have here is a log base 10, 10 equals x. If I do ELB on this, I'm going to get 10 to the x equals 10. I'm going to put a 1 there for convenience. Again, if the bases are the same, the exponents are equal. So for B, I get x equals 1. For part C, this is a little interesting. You'll notice that the base is actually larger than the argument. Look, you'll see what happens here. So if I go ahead and rearrange this, we get this set up. The 8, of course, is going to break down to 2 to the 3rd power. The bases are the same. So we set the exponents equal to each other. We solve for x. And we get x is 1/3. So notice that in this case, if the base is less than the argument, your logarithm is going to be less than 1. It'll be a fraction, it'll be a decimal, less than 1. Recall that a natural logarithm, the base is e. So I'm going to rewrite that natural logarithm as a log base e. And I'm going to go ahead and do ELB, right? The exponent is the logarithm of the base. The base is e. The exponent is x. Consider for a moment what power of x would give you a value of 1. Well, that's only going to be possible if x is 0, because anything to the 0 power is 1. Again, recall that natural logarithm is log base e. The argument is e. We do ELB on this. I get e to the x equals e. Of course, you'll note that the bases are the same, therefore the exponents are equal. X equals 1. And finally, this funny fellow. So we do ELB on this one. We get that the base is 1/3. The exponent is x. And the argument is 27. Now, we'll have to do what we've done before in the past. This is going to be 3 to the negative 1. We have to be comfortable with our use of exponents. 27 is 3 to the 3rd power. The bases are the same. And we evaluate that one as well. We have evaluated these 6 examples for you. For your summary, what are some concepts you learned about exponentials that served you in this lecture video? Take some time to reflect on that.